Final topic for Chapter 9, Kinetic Molecular Theory. Okay, so kinetic molecular theory is a theory that describes how gases work, right? What is going on for gases. And if we break down the name, it's kinetic. So kinetic is, remember, the energy of motion. So this is going to be all about the fact that molecules are moving constantly and that they are made of molecules. So the kinetic molecular theory of gases is historically extremely important. For our purposes, we've already used a lot of the ideas of kinetic molecular theory. Here are the 5 main tenets of it. A couple of them, one, that there are no significant interactions between particles, and that gas particles are much smaller than the distance between them. Those are the ideas from the ideal gas law, right? The idea that no significant interactions, well, in an ideal gas, there are no interactions, and that gas particles are much smaller. In an ideal gas, they have no size, right? They are infinitely small. And so these ideas are things we've already used. Other parts of it, the average kinetic energy of particles is proportional to the temperature. That's just our definition of temperature back from chapter 5, right? These ideas. So kinetic molecular theory of gases is really important historically, and we already have actually used a bunch of the parts of that come from kinetic molecular theory. One of the things is that molecules exist. So we've used those ideas without kind of really talking about it. So we're just going to talk about a little more of the parts of kinetic molecular theory and a little more on the implications, right? I just showed photos of gas particles in constant random motion, or GIFs, right when we started this chapter. And then that third point, that there's no loss of kinetic energy when gas particles collide, that's related to number 2, that basically there are no significant interactions. That the idea is when they hit each other, they just bounce right off. They don't slow down. They just keep going. So if we want to think about some of the implications of this, kinetic molecular theory implies that kinetic energy is what we'd potentially want. And our equation for kinetic energy is equal to 1/2 times the mass times the velocity squared. Okay, so this is the kinetic energy of any object in motion. And so if we want to look at these two sides, first off, the kinetic energy side. We know that temperature determines average kinetic energy of any substance. And so if you have 2 gases that are at different temperatures, the one that is at a higher temperature has higher kinetic energy. But 2 gases at the same temperature have the same kinetic energy. So kinetic energy is all about temperature. Once you have the temperature set, that fully determines the kinetic energy of whatever the gas is. Doesn't matter what type of gas you have. Again, it doesn't matter what the gas is. That higher kinetic energy is just based on temperature. So the other side, though, mass comes in. And mass depends on the type of molecule that you're dealing with. So we can see that this kinetic energy is just locked by temperature. So once you have a temperature, on the other side of the equation, you have the mass and you have the velocity. So if you have a higher mass, the m term is bigger, so the v term has to be smaller. So molecules with high masses have lower speeds, and molecules with low masses have higher speeds. Okay, so this is one of the first implications. Again, this is going to be something that depends on the type of gas that you're dealing with. If you have a gas with a high mass, when I say mass, I mean the molecule mass, there are going to be slower speeds of those molecules. Low mass molecules have higher speeds. So we can look at the effects of this. So at room temperature, so 25 degrees Celsius, that's 77 Fahrenheit. So helium gas, when we say it has a low mass, we can measure that using the molar mass. So helium, its speed is about just over 1,000 meters per second. It's the same as 3,000 miles per hour. Nitrogen gas is going just over 1,000 miles an hour. Sulfur hexafluoride, so this would be a pretty heavy as far as gas molecules go. It's at about 500 miles per hour. So one of the things to take away from this is when we see that inverse relationship, that as the molecules get bigger and bigger, their average speed gets lower and lower. They're moving slower and slower. But they're all still moving extremely fast, right? These molecules are zipping around, right? Sulfur is a pretty heavy, sulfur hexafluoride is a pretty heavy gas there at 146 grams per mole. The speed is still 500 miles per hour. And so gas molecules are moving so fast that when they collide, they just are bouncing right off each other. They don't spend a lot of time next to each other because they're moving so fast. And so this really, really high speed of gas molecules is why we can assume that gas molecules don't have interactions with each other, and it's a justification for why we can assume that real gases behave like ideal gases, because real gases are moving so fast that the molecules don't have time to establish any sort of interaction. It doesn't matter if they want to interact, they're not going to. So we can just treat real gases as if they're ideal because they just are moving so very fast. Okay. So another thing we want to look at is the volume of a gas molecule. Again, we said that molecules were really small, right? That's one of the kind of the other part of the ideal gas is that these molecules are so small. In an ideal gas, they have no volume, right? The molecule has no volume at all. So let's take a look at some of the volumes of gas. So first, we can use the ideal gas law to figure out the volume, total volume of a gas sample. And we can rearrange PV over RT. Plug it in for conditions, we'll say 1 atmosphere pressure and again room temperature, so pretty standard conditions. That's a pretty good approximation of the air you're currently in. So that's the total volume. So if we have that many moles, we know that's how many molecules are in there. So in 1 liter of gas, you have 2.5 times 10 to the 22nd molecules. So what about the total volume of the actual molecules themselves? So a molecule has a volume of about 10 to the negative 27 liters. And so if you take your total molecules and multiply it by the volume per molecule, you get the total volume of the molecules themselves. That means this is the volume of the actual atoms that are making up this gas. So quite small. Whereas this is all the volume, including empty space between the molecules. And so if we take that ratio, we can see that the volume of all the molecules divided by that total volume is quite a small percentage. So if you have a sample of gas, over 99% of the volume of that gas is really just empty space between the molecules. So this is why we can make this argument that, a real gas just is approximately an ideal gas where the molecules have no volume because they're just so small and there's so much empty space between all those molecules. But yes, they're not actually, we know atoms have a volume, they have a size, they have shape, all sorts of stuff like that. But when it comes to relative volume in a gas, the molecules and atoms themselves are a very, very small component. It's mostly just empty space. So this is why we can just assume these ideal gas tenets. We can use the ideal gas law to describe real gases because they move so fast, they don't have interactions with each other, and they're so small and there's so much empty space that you might as well just say that they have no volume. Okay, so these kinetic molecular theory of gases, we can also use it to understand kind of the why behind all the different gas laws we've talked about. We already understand the why we can describe gases as ideal. So what about the named gas laws? So we have Daltons Law, which said that pressure and temperature were directly related. And we can understand the reason for that is that as you increase temperature, you get higher kinetic energy and the gas molecules move faster. Since the molecules move faster, they will collide more strongly with the walls of the container and you increase the pressure. For Boyle's law, as you decrease the volume, you make the walls of the container closer together. What that therefore implies is that it's easier for the molecules to hit the wall. The temperature doesn't change in Boyle's law, right? So the molecules are moving with the same speed, but importantly, they are just hitting the wall more frequently. The number of collisions increases, so that means your pressure goes up. For Avogadro's law, that would be that the number of molecules is directly related to volume. Again, same idea. You're at a given temperature. You just have more molecules. Because you have more molecules, there's more collisions. One of the big takeaways from kinetic molecular theory is that pressure only depends on just the number of collisions. More molecules means more collisions. If we look at, say, a gas mixture, Dalton's law, gases just randomly move around, right? They don't interact with other gases, even if those gases are, say, the same type. 2 nitrogen molecules don't interact with each other. A nitrogen molecule and an oxygen molecule don't interact with each other either, okay? And so when we take gases and they're by themselves, they have a certain temperature, those molecules are going to be colliding with the walls in a certain way. If we mix other gases in, because they don't interact with each other, it's not going to affect how those molecules collide with the container, okay? And so for a given temperature, pressure only depends on the number of molecules. More molecules you have, the temperature, you're locked in your speed, so the more molecules you have, they're going to be flying, they're just more molecules, you're just going to get more collisions. The collisions are going to be the same strength, there's just more of them. Fewer molecules, lower pressure, more molecules, higher pressure. We want to look at a fusion now. When we talk about a fusion and we make the argument or state the law that lighter gases effuse faster, people have a tendency to think that it's the smaller gas, that the smaller molecule can pass through the hole more efficiently because it's smaller. But really, when it comes down to a fusion, the molecules are so tiny for any type of gas that the hole that you're passing through is like the size of a pen. You could fit billions of molecules in that hole. It really does just come down to the fact it's all this kinetic molecular theory. And then if you have a smaller molecule, the molecule is just moving faster. The molecules all have the same kinetic energy for a given temperature. And so lighter molecules just have higher speeds and therefore faster effusion. The lighter the molecule is, the faster it moves, and you're going to get more efficient effusion.